The Boeing 747 is one of the most iconic aircraft ever built, a technological marvel that changed global travel forever. But what most people don't know is that deep within its massive wings lies a surprising and unsettling secret, one that involves a radioactive metal few would ever expect to find in a passenger jet. It's a story that blends innovation with danger, engineering genius with hidden risk, and sheds light on a time when the race for performance overshadowed the long-term consequences of certain design choices. To understand how and why this happened, we have to go back to the golden age of aviation engineering, when speed, strength, and endurance were everything. During the late 1960s, Boeing engineers faced an enormous challenge: designing a jet large enough to carry hundreds of passengers across continents, yet light enough to remain efficient. The new 747 would need wings that could flex, handle massive loads, and endure extreme stress. Aluminum, while lightweight, wasn't always strong enough for key structural components, especially near the engines and the inner wing spars. That's when engineers began exploring exotic alloys, including thorium-infused magnesium, a metal known for its impressive strength-to-weight ratio and resistance to heat. Thorium, however, is slightly radioactive. At the time, this wasn't as alarming as it sounds today. In the 1950s and 60s, thorium was widely used in aircraft engines, gas lantern mantles, and even camera lenses. Its weak radioactivity was considered negligible, especially when sealed within metal structures. The goal was to make aircraft parts lighter and more heat-resistant, vital for the new generation of jetliners that would fly higher, faster, and farther than anything before. Boeing and other aerospace manufacturers began experimenting with magnesium-thorium alloys for critical structural components like wing edges, engine casings, and landing gear brackets. The problem? Over time, as environmental and health standards evolved, regulators began realizing that the very materials once praised for durability could pose serious risks during maintenance, scrapping, or crashes. When these alloys are cut, ground, or burned, they can release radioactive dust and particles. That means mechanics, recyclers, and even scrapyard workers handling decommissioned jets could be exposed without ever realizing it. For Boeing's engineers, the inclusion of such materials wasn't about negligence, it was about pushing limits. The 747, first flown in 1969, was a marvel of engineering, but it represented the peak of Cold War-era design philosophy: performance first, risk later. Many aerospace manufacturers, including Lockheed and McDonnell Douglas, also used similar alloys in aircraft of the era. But as decades passed and the aviation industry grew more transparent about material safety, the presence of thorium in certain parts of older planes began to raise eyebrows. Today, most modern aircraft avoid these alloys entirely. Composite materials, carbon fiber, and advanced aluminum-lithium alloys have replaced radioactive metals. Still, that doesn't erase the legacy of what came before. Many older Boeing 747s, now stored in boneyards or dismantled for parts, may still contain trace amounts of thorium alloys in their wings and engine mounts. While these pose virtually no threat during normal operation, they become a concern during disassembly or melting. That's why aerospace scrapyards handling 1970s and 1980s era aircraft must follow strict handling procedures, and in some cases undergo radiation checks before recycling parts. Interestingly, thorium isn't the only hidden hazard in aircraft manufacturing. Other materials used across the aviation world, like beryllium, cadmium, and asbestos insulation, were once considered essential for performance, but later discovered to be toxic. This shows how industrial innovation often walks a fine line between progress and peril. Engineers of the past were working with the best data they had, unaware of the long-term implications that would later reshape safety protocols. One of the most fascinating aspects of this story is how few people actually knew about the presence of radioactive materials in aircraft. Even pilots and airline operators often had no idea. These details were buried deep within material specification sheets and engineering blueprints. It wasn't until the decommissioning of military jets and early 747s that the question began surfacing: what exactly are we melting down here? Studies conducted in the early 2000s revealed measurable, though minimal, levels of thorium radiation in specific magnesium alloy components. While far below dangerous thresholds, the discovery reignited debate over legacy aerospace materials. The situation also highlights an intriguing contradiction. Thorium itself, as an element, is now being researched as a potential fuel for clean nuclear reactors, a safer alternative to uranium with less long-term waste. Yet, the same element, when used in aircraft alloys decades ago, is now treated as hazardous. It's a reminder that context is everything. What once symbolized progress can later represent risk, depending on what we know and how we handle it. Aviation historians argue that this chapter of the Boeing 747's history underscores the relentless push of human ambition. When Boeing engineers set out to create the jumbo jet, they were rewriting the rules of flight. Every gram of weight mattered. Every material innovation could mean the difference between success and failure. The introduction of thorium alloys helped achieve the incredible lift-to-weight ratios that made the 747 possible. Without such risks, it's arguable that commercial aviation wouldn't have advanced so quickly. Even today, the story doesn't end. Many of those 747s, particularly cargo variants and early passenger models, are still flying. Their wings, composed of countless layers of aluminum, titanium, and specialized alloys, continue to carry millions of pounds of cargo and passengers across the world. While the thorium content poses no operational danger, the awareness of its existence has led to more thorough maintenance protocols and recycling standards. The FAA and EPA have since issued advisories ensuring safe handling when these planes reach end of life. This hidden history also opens up a broader conversation about engineering ethics. Should the use of slightly radioactive materials have been disclosed more publicly? Were the risks truly negligible or simply underestimated due to lack of data? These are the kinds of questions that modern aerospace design now takes seriously. Transparency, environmental responsibility, and long-term safety are no longer optional. They are foundational. Boeing, Airbus, and other manufacturers now rigorously test and certify every single material used, ensuring full life cycle accountability. The 747's hidden radioactive metal serves as both a symbol of innovation and a cautionary tale. It represents an era when engineers pushed the boundaries of physics and materials science to achieve miracles of flight, but also when the understanding of material safety was still evolving. The thorium alloys inside those wings remind us that technological greatness often carries invisible costs that only future generations can fully understand. As the aviation world moves into a new age, one dominated by electric propulsion, composite materials, and environmentally responsible design, stories like this remain vital. They show how far we've come, not just in engineering, but in awareness. The Boeing 747 will always be remembered as the queen of the skies, but within her design lies a fascinating paradox. One where the quest for strength and efficiency intersected with the unknowns of science. In the end, the story of the radioactive metal hidden in the Boeing 747's wings is less about fear and more about evolution. It's a testament to how innovation never stands still, and how even our most brilliant creations can carry lessons that shape the safer, smarter technologies of tomorrow. But the real question is, why on earth would engineers willingly choose to build part of a passenger aircraft using a radioactive material? The answer, as surprising as it sounds, comes down to physics, durability, and performance. In the early days of advanced aerospace engineering, materials like thorium and uranium alloys were seen as technological marvels, incredibly strong, heat-resistant, and lightweight compared to traditional aluminum or titanium. These properties made them ideal for use in jet engines, turbines, and high-stress wing components, especially before modern composites became mainstream. Thorium, in particular, was used to create high-temperature alloys that could withstand conditions that would melt or warp most metals. It was also slightly radioactive, but its decay rate was so slow that it didn't pose a health risk unless mishandled. When combined with magnesium or nickel, it offered extraordinary strength-to-weight ratios, which helped make early long-range aircraft both safer and more efficient. In the 1960s and 70s, engineers were in a race to push the limits of aviation: higher altitudes, faster speeds, and longer distances. Aircraft like the Boeing 747, which was designed to carry hundreds of passengers halfway across the world, required unprecedented engineering innovations. Boeing engineers explored dozens of material combinations for the wings, areas of the plane that experience immense mechanical stress and fluctuating temperatures. While the outer structure was primarily aluminum, certain components inside the jet engines and support assemblies were made with alloys that contained trace amounts of thorium. This wasn't done out of carelessness. It was a bold step toward achieving greater performance and reliability. However, decades later, when retired aircraft were being dismantled, technicians began noticing unusual readings on Geiger counters, faint but unmistakable signs of radioactivity. These readings sparked curiosity and concern. Investigators traced the source to certain engine parts and coatings used to prevent oxidation and enhance heat resistance. What they found opened a forgotten chapter in aerospace history, a time when scientists and engineers balanced innovation with risk in ways that seem almost reckless by today's standards. To understand why thorium found its way into aviation, we need to look back at the Cold War era, when nuclear technology was synonymous with progress. During this time, the US and its allies were exploring every possible application of radioactive materials, from energy to propulsion. There were even projects to design nuclear-powered aircraft, capable of flying for months without refueling. Although such aircraft never reached operational stages due to safety concerns, the research led to valuable discoveries in radiation-resistant alloys and heat-dissipating materials, which later influenced commercial jet manufacturing. Interestingly, thorium's role in aviation wasn't limited to metals. It was also used in lamp mantles and cathodes for electron tubes, providing stable performance under extreme conditions. In aviation electronics, durability and resistance to temperature fluctuations were essential, and thorium offered those benefits. In small, sealed quantities, it posed little immediate threat. The problem came years later, when maintenance crews or recyclers were unaware of its presence. As environmental and occupational safety standards evolved, manufacturers began phasing out such materials. By the 1980s, Boeing and other aerospace companies had shifted towards safer alternatives, including titanium alloys, carbon composites, and ceramic coatings that achieved similar performance without the radioactive trade-off. But even today, aviation historians and engineers occasionally uncover remnants of this experimental phase in old and ethical reflection. What once symbolized human progress has now become a historical curiosity, a tale of how close we came to blending nuclear science with commercial flight. In the end, the metal hidden in those wings wasn't just radioactive, it was symbolic. It represented humanity's relentless desire to reach farther, faster, and higher, no matter the risks. And while we now fly on safer, smarter machines built from carbon fiber and nanocomposites, the spirit of those early engineers, bold enough to mix radiation with flight, continues to shape every new leap in aerospace innovation.